Much of the control theory relies on linear models. If we develop a nonlinear model, let's say from an energy balance that has some nonlinear terms in there, like radiative heat transfer, we can't apply a lot of the linear systems theory. So we need to linearize it, and we're going to cover in this video how to linearize an expression and get into a standard form that we can use it. So first of all, when we're linearizing an energy balance that includes convection and radiative heat transfer, it's going to include terms such as our convection and radiation. And then these are just constants, the MC sub p, and the alpha is a constant. And we're going to linearize this with respect to temperature and to the Q value. So let's just review the linearization formula. We're going to put everything onto the right hand side, and then we have f of t comma q. We're going to use a Taylor series expansion. Now we don't have our first term there, which is f of t. I'll put the bar over it, and q with the bar over it. That just means that steady state values. That first term is going to be 0 if we choose steady state values for our point of linearization, because the derivative is 0 at the nominal values. So we don't need that first term. And then we could add some additional Taylor series terms as well. Okay, if we wanted to, and then it'd be 1 over 2 factorial, and then q minus q bar squared. And then we could do the same for the other ones as well. We're not going to do that. We're just going to do a linear approximation, so those higher order terms are 0. If we put this into condensed form, we're going to take this and say that that is gamma value, and then this term right here, and that one is going to be our beta value. So it's just going to be constants once we plug in the nominal values after taking the derivative of this right hand side of the expression with respect to temperature and with respect to Q. So there's some more information on the course website that reviews the linearization and how we do that. But just to give application here, we're going to say our gamma is that right hand side of the equation. We take the derivative with respect to t, and then we plug in the nominal values there of t bar and q bar to our steady state conditions. Okay, and then we're going to use these values right here: alpha, TA, m, epsilon, a, c sub p, u, sigma, which are Stefan-Boltzmann constant, and then t infinity. Okay, we're going to adjust the heater to 75% over 5 minutes, and we can take the solution from the prior TCLab and then add to it, okay, and then we'll simulate it. So let's go ahead and just do the linearization of this this formula that's here on the right. We're going to start with this, and then we'll add it to the code, and then we'll run it. So here is, let me go ahead and just erase some of this. Alright, and we'll start with a clean one, and so I'm going to take the derivative here with respect to temperature. And so if I just take the derivative of this right hand term, okay, derivative with respect to temperature, then I'm going to be left with something that is UA. Alright, and then let's see, it's going to be negative UA and divided by MC sub p. Alright, and then on this term right here, when I take it with respect to temperature, that's going to be minus epsilon sigma a, and then I have a 4, and then that's going to be temperature to the third, and then that will be also be divided by MC sub p. Now I'm going to be plugging in the nominal value there, which is the bar, and then this is going to evaluate to a constant. Let's go and do the next one as well. This is our beta value, and that one is a little bit easier. It's just going to be alpha divided by Okay, oops, alpha divided by m c sub p. Okay, let's go ahead and just plug those into our code now. We're going to simulate this, where this is our differential equation. We want to simulate that together with the nonlinear expression that we had from the prior example. Okay, so I'm going to add this to the script that we had that combined our radiative and our convective heat transfer. Also collects the data, so we'll be able to compare all of them together, see how much they're different. Okay, so I'm going to add down here, okay, I'm going to convert it into Kelvin, the ambient temperature, add 273.15, and then I'm going to have my gamma value, and that's going to be negative U times A minus 4 times epsilon times sigma times A times TAK, okay, at the ambient temperature, which is my nominal steady state condition. And I'm going to divide by mc sub p, which is the mass times the heat capacity on both sides. So there's my gamma value. And let's do the beta value as well. And that's going to be alpha divided by m times c sub p. So I have my linear expression there. I only have two constants, gamma and beta. And I'm going to define my simulation model. And I have t sub c and t. TC is what we had in the prior example. We actually have to do two states now. So let's go ahead and make that x. And then we're going to divide that into two states, the temperature of the nonlinear, which is TC, this one right here, and then the temperature of the linear, which is going to be TC2. So I'm just going to break that. This is going to be a list of two, and it's going to break it into these individual ones and assign it on the left-hand side. I want to convert those to Kelvin. Okay, TC, I got to convert that to Kelvin. The other one I don't need to. Okay, here's my nonlinear expression. Make that a little bit wider so it shows up on one line. And then my linear one is going to be dc2 dt, and that's going to be equal to gamma times tc2 plus beta times q. And one thing that we need to remember is these are in deviation variable form, as shown here on the left. Okay, those temperatures in Q values, they have the prime, which means you always subtract the nominal value from those. So don't forget that in the linear model. It's a very common mistake. Okay, so just subtract 23, which is my nominal value, and the Q is just 0. So when the heater's off, we're going to say that we're at 23 degrees. Those are my steady state conditions where I linearized. Okay, then I'm going to need to return not just the dct dt, but let's also return the linear derivative as well. And then we have our time for integration. And tsim is going to be ODE int of lab sim, and then I put in my two initial conditions, and then the time. So it's going to integrate both of those differential equations with one function. That's our model, and then I just need to split out the results of tsim. Instead of being just one vector of values, it's going to have the first column is going to be tsim. So this colon means take all of the rows and then take the very first column, and then the next one is take all of the rows but the second column, and that's going to be my linear temperature. Okay, now I'm going to add my nonlinear right here to the plotting, and then my linear. Okay, so that's it. Let's go ahead and just simulate this now. We have, just to summarize, we have our linear differential equation and our nonlinear, and we're going to compare those with, if we're connected to the measured values. So the measured values are the same as they were before. We're going to collect it from the Arduino by getting the T1 value, lab.T1, over and over again for 300 seconds, and then just compare that with the solution. Okay, so let's see. I'm going to go ahead and just open this with ODE int. You could run this in Jupyter Notebook as well, or Spider, or any other Python environment. And it's going to connect to the TCLab, and then you're going to just see some values are printed out. So we started right around 20, We assume 23, so it's going to be off just a little bit. But we're going to turn on the heater to 75% and make sure we just had that here. Let's see, our Q value. Oh, I have 50 right there. I think I should have done 75%. Let me go ahead and just shut this off. I'll go ahead and stop it. Let's see. Quick adjustment here. Let me do 75 instead. Alright, I'll turn it to 75, and then let's just make sure this is 75 too. Okay, for the heater, it's going to start just a little bit hotter just because I had it on for just a little bit just to start. Ooh, I think I need to cool that off. I'm going to pause the video, cool off the heater a little bit, and then we'll start it again. Okay, so I brought the temperature control lab device outside for a little bit. It's October, and it's a little bit cool. So hopefully this will have cooled it off, and let's run it again. See if it's back around ambient temperature. And we're going to go up to 75% instead of 50. Oh, it was a little bit cold outside. We'll just see how this works. 16 degrees Celsius, and you'll start tracking up, and then we'll just compare the nonlinear to the linear, and also compare both of those to the measured values. Now, one of the things that as this is starting to collect, I ran this before, and here were the results from before. You can see the nonlinear and the linear, and then the measured values. This was with 50% heater output, so it's going to be 75 now, which is going to get to a higher value. It's going to trend up maybe 70, 80 degrees Celsius instead of down at 55 or 60. And you could see the linear versus the nonlinear. The linear is a little bit higher than the nonlinear, especially in this area right at the end. And so thinking about that, why would they deviate that way? Why would the nonlinear be a little bit lower than the linear? I think it's because of the nonlinearity, which is the radiative heat transfer has a temperature to the fourth dependence. So the linear model was linearized right around 23 degrees Celsius, but when it rises up to higher temperature, it's going to underpredict the amount of heat that's lost through radiative heat transfer, and so the temperature of the linear model is going to be higher. Okay, and so you can see that in the plot. It's not an incredibly nonlinear system. If it were, the gain would change by quite a bit, but here there's just a slight deviation between the linear and the nonlinear. So I'll go ahead and pause it now, and then we'll pick it back up once the 5 minutes with the 75% heater is done. One thing to just watch out for is, if it gets above 100 degrees Celsius, there's a safety thing built in, so it'll automatically shut off the heaters. Even though they can go much higher, just for safety reasons, they'll automatically shut off. But let's just go ahead and see what those are, and then we'll pause it. Okay, so it's about 50 degrees Celsius right now. It's continuing to rise. So here's the solution that it came up with. It just completed. You can see the highest temperature was about 67, and this one started a little bit lower and then heated up. You can see they're kind of parallel to each other. You can see even at higher temperatures there's a little bit more of a deviation between the two. The nonlinear looks like it's going to level out somewhere closer to the measured temperature. If we used an ambient temperature in the nonlinear of 20 and started both of them at 20 instead of 23, they'd also be closer in the end. Okay, so there's the simulation, and you can see the differences between the two. Okay, and let me just explain a little bit about the overview of where we're going with this right now. We have this as the fourth of many on the temperature control lab. So I just want to go back to the overview and draw a little bit of a map about why we're doing these things. So for a controller, when we're developing a controller, we need to come up with, for a PID controller especially, we need to have Kc, tau I, and tau d. Those are going to be some of the constants, and to get those, we use a tuning correlation that can be dependent on our model of our system. So we need some sort of a model, and one simple way to do that is to come up with Kp, tau p, and theta p, like a first order plus dead time model. And there's multiple ways of getting this model. One would be like a physics-based approach. Okay, a physics-based method. Okay, and if it's nonlinear, then we may have to linearize and then get it back into FOPDT form. If we just have some data, then we can take two approaches. We can either do a graphical fit to a step test, or we can do another approach, which would be a regression approach. Okay, and then get our FOPDT model. If we have a nonlinear physics-based model, the other thing we do is we can just simulate. Okay, so we can just simulate step responses or a doublet test and get kind of fake data and then do a graphical or regression method. So in the case of this has been exercise 1, 2, 3, 4, 5, and 6. It's all kind of in the modeling area. So the first one was just simulating. Okay, that was number 1 on this list. How do you simulate a model and be able to produce a predicted response? The 2 and 3 were about developing this physics-based model. Okay, and then we just did linearize, which is number 4. And then number 5 will be the graphical method for obtaining models. And then number 6 on this list is going to be regression. And then later we're going to do 7 plus. That's going to be able to get tuning parameters implemented on the controller.